Welcome to the module on GIS in sanitation planning. Hi, I am Karthik. I work with Wash Institute. In this module, we will understand what is Geographical Information System, its key features and attributes, examine its role throughout the sanitation value chain and how it can be utilized for effective analysis and planning. GIS stands for Geographic Information System, where geography is the study of the earth, information involves capturing, analyzing and interpreting data, system is a set of software tools. Thus, Geographic Information Systems aids in studying the earth by capturing, analyzing and understanding the information within a spatial context. Let us look at the key features of Geographic Information System that makes it essential for effective urban planning and decision making. GIS facilitates spatial analysis by examining geographical patterns and relationships such as land use, zoning and infrastructure distribution, enabling informed decisions about urban development and resource allocation. It enables the creation of detailed, interactive maps for mapping and visualization of data such as population density, transportation networks and environmental impacts, helping stakeholders understand complex information and make informed decisions. Furthermore, GIS supports data integration by combining information from various sources such as census, environmental data and traffic data into a single platform. This comprehensive view enhances analysis and decision making. It also supports scenario modeling, allowing users to simulate different urban development scenarios and assess their potential outcomes and evaluate the impacts of proposed changes before implementation, reducing risks and improving planning accuracy. In addition, GIS facilitates public participation by providing accessible maps and data for community feedback. This transparency encourages public input and helps ensure that urban planning decisions reflect the needs and the preferences of the community. It supports the tracking of ongoing developments and changes in real time such as construction progress, traffic conditions and environmental changes. This capability allows for timely responses to issues and improves system management. Finally, it aids in infrastructure planning by enabling precise planning and management of urban infrastructure such as roads, utilities and public services. Using spatial accuracy, planners can optimize infrastructure placement and design. To understand how GIS captures information spatially, let us start with how we reference a point on Earth. A point on the Earth is identified by its longitude and latitude coordinates, which are angles measured in degrees. Latitude is the angle measured from the equator, while longitude is the angle measured from the prime meridian. Using these coordinates, GIS software like Google Earth and GPS-enabled tools can accurately map point and linear data using projection systems. The information collected from the Earth's curved surface is then digitized into a flat map or spatial 2D representation similar to flattening an orange peel to view its surface. Now, let us explore how GIS can help in used water management planning. Let us begin by understanding sanitation value chain. It involves several key stages that ensures the effective management of used water. It starts with the user interface, where the waste is initially captured, followed by containment and emptying. The waste is then transported or conveyed to the treatment facilities. After treatment, the process concludes with either disposal or repurposing for end use, ensuring that every stage contributes to sustainable sanitation. GIS is quite useful in mapping the data and analyzing each stage of sanitation. In the user interface stage, GIS maps and analyzes the availability of toilet facilities across a region. It helps in assessing the sufficiency and placement of shared sanitation facilities such as community toilets. It also helps to identify toilets vulnerable to natural disasters like floods, earthquakes or landslides. In containment stage, GIS provides a detailed visual database of containment systems capturing critical information such as size, capacity and desludging frequency. Followed by, in the emptying stage, GIS helps identifying locations of different types of containment systems, aiding in scheduling and route mapping for desludging operations. In the transport stage, GIS helps in mapping the existing sewerage network. It enables planners to design and optimize new sewerage networks, ensuring they are cost effective and meet future population needs. GIS also assists in creating optimal routes for desludging vehicles, minimizes travel time and cost. By analyzing the characteristics of containment systems, GIS helps determining the appropriate size of desludging vehicles for different areas. Additionally, it allows for real-time tracking of desludging vehicles, ensuring they follow planned routes and schedules. In the treatment stage, GIS aids in selecting suitable sites for sewage treatment plants and fecal sludge treatment plants, considering factors like land availability and environmental impact. It also allows planners to assess the vulnerability of treatment infrastructure to natural and human-induced risk, ensuring the resilience and reliability of these facilities. Furthermore, GIS supports long-term planning by identifying potential areas for future expansion. In the safe reuse or disposal stage, GIS maps the locations of end users who will utilize treated waste products. It also analyzes the distance between the treatment facilities and the end users to plan the most efficient conveyance routes, reducing cost and ensuring timely delivery of treated products for reuse or disposal. GIS also supports the analysis of collected data in several key areas. GIS technology can accurately pinpoint entities such as households, business or industrial facilities that contribute to environmental pollution as polluters. GIS also helps to map and locate households generating used water. By using storm drain network maps from walkthrough audits or satellite imagery, GIS helps locate endpoints of drainage system. It further analyzes topographical survey data and drain flow mapping to determine the catchment areas for a drain-based used water treatment. GIS estimates the volumes of used water being discharged into various systems, including on-site disposal methods, storm drains, and open land or water bodies. It calculates drain flow rates during peak hours and heavy rainfall. Additionally, GIS helps to analyze the impact of extreme weather events such as heavy rainfall and flash floods on sanitation infrastructure. Now, let us look at how GIS can be used for various aspects of sanitation planning. GIS is a powerful tool for spatially mapping and assessing data. It plays a key role in the analysis of toilet accessibility. GIS and Google Earth can be used to map households and establishments such as public toilets and community toilets. Additionally, GIS helps identifying toilet accessibility and usage, along with available facilities. It also assists in analyzing the reach of PT and CTs, ensuring they are built according to CPHO guidelines such as being within 500 meters of any public space. For containments, GIS can aid in developing a comprehensive database of containment systems on maps, playing a critical role in optimizing sanitation management. By mapping out various types of toilet containment systems such as septic tanks with outlets connected to drains, single leach pits, and households without individual toilets, authorities can efficiently identify and determine specific action points for each system. For example, the database can pinpoint the exact locations of insanitary toilets within a town, highlight systems that requires retrofitting, and identify areas where periodic desludging needs to be enforced. Similarly, developing a water connection database with GIS technology helps in optimizing water supply management and ensuring equitable access across communities. By systematically categorizing and visualizing different water connection types such as double hoses, water stand post, individual connections, hand pumps, and shared water connections, the authorities can efficiently identify areas with specific needs. For example, the database enables the identification of shared water connections that may need upgrades to individual systems, maintenance requirements for hand pumps, and regions lacking sufficient information that warrant further investigation. GIS can assist in planning for the emptying and transportation of fecal sludge by developing an understanding of accessibility of containment systems through road width analysis. Mapping challenges or issues such as road condition improvements or incorporation of community level collection systems or procurement of appropriate size of desludging vehicle to navigate the area. Estimating time required for desludging operators to reach various locations at the district and block levels, and monitoring the movement of desludging vehicles to ensure they dispose of the sludge properly at the designated treatment facilities. Optimizing FSTPs and STPs is a key to efficient and sustainable waste management. GIS can aid in this. Let's look at an example. This map illustrates the blockwise percentage of latrines that have never been desludged. Dark purple blocks indicate high percentage of latrines that have never been desludged, highlighting poor desludging access, while blocks with the less percentage of latrines that have never desludged indicated by lighter shades. The next map depicts the blockwise percentage of households that are accessible by road using a tractor or small truck. Blocks with good accessibility for tractors on small trucks indicated by darker shades of blue, while others, particularly in more mountainous areas, have limited accessibility indicated by lighter shades. Analyzing both maps reveals that blocks that are well connected by road tend to have better access to desludging services, whereas blocks with limited road access have higher percentages of latrines that have never been desludged. GIS applications can significantly enhance the FSTP and STP operations and the desludging activities by clustering of regions or area with high desludging demand that are within 15 to 20 km of the existing FSTPs or STPs, selecting optimal routes based on road quality, road width, geographic constraints to improve travel efficiency, identifying the time required by the desludging operators to reach a certain distance at a district and a block level that helps in assessing the optimal travel cost. Let us see an example of using GIS for siting a FSTP. When selecting a site for an FSTP, certain factors need to be considered. The map highlights one crucial factor, which is the population density in a service coverage stretch of a town. Areas indicated by darker shades represent high population density, while the lighter shades indicate less populated regions. Fecal sludge treatment plants should be placed away from densely populated areas to reduce environmental and health risk, while maintaining efficient waste collection with minimal transportation cost. The highlighted green area on the map indicates a suitable site for an FSTP due to the lower population density surrounding it. By utilizing Google Earth and GIS, selecting the most suitable sites for fecal sludge treatment plants becomes more efficient, ensuring optimal placement and adherence to guidelines. These tools facilitate in mapping existing routes and available open spaces nearest to the area having high demand for desludging. They also assist in filtering the road based on accessibility for small, medium and large desludging vehicles and identifying government owned available open land to select optimal site. Additionally, they aid in selecting optimal sites according to Pollution Control Board norms and guidelines, ensuring appropriate distance from nearby habitats and for their end use. Similarly, selecting a site for sewage treatment plants requires careful consideration of various factors such as topography, proximity to water bodies. The map highlights the variations in elevation and the extent of water spread. Higher elevation areas are depicted in darker green shades, while lower elevation areas are shown in lighter shades. Water spread is represented in the dark blue. An ideal STP location is a lower elevation near a water body, using natural land gradients for efficient used water flow. The setup allows used water flow naturally downhill, reducing the need for pumps and allows easy discharge of treated water into the water body. The yellow point on the map shows a suitable area for location of an STP due to the lower elevation and proximity to a water body. The map highlights the suitable sites within a marked area indicated by yellow lines. GIS can be used to identify suitable sites for sewage treatment plants by analyzing topography, available open land, and other local constraints like environmental regulations, proximity to population centers, and utility infrastructure. Additionally, GIS can assist in selecting the appropriate conveyance systems, designing infrastructure for inflow and discharge as needed, and determining best locations for pumping stations based on the requirements. Using topographical analysis, ground surveys, and walkthrough inspections of drainage systems, GIS applications can effectively identify the catchment areas of existing drainage infrastructure. This involves assessing factors such as natural slopes, elevations, and micro-level flooding or structural changes. Identifying catchments for drainage endpoints helps find areas that are not well connected and need improvement. Mapping these catchments also helps create distinct zones within the town and make better decisions on effective and affordable solutions to cover all areas. GIS can help in mapping probable impact of disasters or hazards such as heavy rains, backflows, floods, and landslides. This mapping helps identify effective measures to prevent and mitigate the impacts of these disasters or hazards. Before we conclude, let's summarize the key takeaways from this module. GIS assists in spatial mapping of collected data, which aids in bridging the gap between data collection, analysis, and spatial planning. It can also help in efficiently analyzing the topography, the slope of the area or region to identify the watershed, catchments, and land use. The GIS software aids in faster incorporation of real-time data into spatial analysis and aids in data correlation. It plays a crucial role in planning for extensive infrastructure projects. It can assist in impact analysis for both climate and human-made factors, which can help in prioritization of critical phases for implementation. Thank you for going through this module.